Okay. In my opinion, and I don't want to bore you with a bunch of stories, engineering stories and stuff like that, but in my opinion, this lesson is where calculus, like the reason for everything that we've been doing, all starts to come together. Um, if you think about anything that's manufactured or anything that's built, like anything at all, like pick this chair, for example, like this plastic back on this chair. Someone had to someone had to design this, someone had to build this, right? It's not just some guy or woman sitting in a like shed cutting this out by hand, right? There's a computer program that does this, right? Or some of you might know, before I became a teacher, I was a civil engineer, so I would design like drainage ditches and stuff like that. Well, when you design a drainage ditch, like you have to know how much, like let's say I'm designing a drainage ditch along a highway, you have to know how much dirt you're excavating, right? Like how are you going to pay someone to excavate your ditch if you don't know how much dirt's coming out? So volume today, when we talk about volume, when we talk about cross sections and revolutions and stuff like that, this is where calculus all starts to come together, and you can kind of see how integration can work in the real world, for example. Okay. You don't have to write any of this down in these first couple slides. I just want to let you know or show you like what cross sections are. When we say cross section is basically cutting through a three-dimensional figure, right? So loaf of bread, each one of these slices is like taking a cross section, okay? And then you take whatever you've cut, it's like looking through it, okay? So it would just be like a kind of like a weird shaped circle. Or let's say you have this river, this drainage, whatever. Let's say you take a big knife and you cut right through it, and then you look into it. It would probably look something like this, right? This would be like the bed of the river. Could look like this, could look like this, however. But this is what we mean when we say cross sections. It means like cutting into a three-dimensional figure, okay? How does that apply to what we're doing today? And again, this is the last slide. You don't really have to write anything down up here. I'm just going to draw you kind of an example of what we're doing today. Let's say you have a graph that has, let's say this is like y equals 6 or something like that. And let's say you have another graph. Let's say this is like an upside down, like negative x squared or something like that. If I were to take this and put it in 3 dimensions, right? Let's say this is my y-axis. Let's say this is my x-axis. This would be my y equals 6. And this would be like my negative parabola or negative x squared graph or whatever, okay? What's that? So the z would be like coming in and out of this board, which we're not going to deal with the z-axis today, but you're right, that would be like this, okay? Finding the volume between these two, or taking a cross section between these two, would mean I am cutting, like let's say I take a square. I'm try my best to be an artist here, guys. I'm not very good at it. Right? Like let's say I take a three-dimensional object like a square and cut right through this. Okay. This width right here would be dx because it's like the width of that knife that I'm cutting through with. This surface area right here, that would give me like the surface area of that knife or that square. If I were to place a bunch of squares between this, right? Let's say this has some depth to it. Now, if I were to connect all those, it would give me some sort of like three-dimensional figure, right? If I took a bunch of, basically, if I cut like infinite amount of cross sections and connected them all together, I could get like a three-dimensional figure, okay? This is the part that you might want to get down in your notes at the bottom. Volume is equal to, from boundaries A to B, the area times dx. So the surface area times the width. Okay, those descriptions underneath it are basically what I just talked about, like the surface area of this times the width of this, the dx, length times width times depth would give you volume. All right. Okay. I've got a handful of examples. I think I've got like 4 or 5 examples here. I'll try to take shortcuts with graphing wherever we can, but basically when we're integrating today, we're just going to do it all in our calculator. We're not going to do any integration by hand, so this will make things quicker for us. And obviously you can use your calculator on the quiz. Yeah. They would be with a calculator, or they would give you simple enough functions that you could quickly do it by hand. Yeah. Okay. Okay, first example, you could write this whole thing down, but eventually I think what you'll find is really like this part right here on all of these examples is what you'd want to write down in your notes. You have a solid whose base is enclosed by the region y equals 0, x equals 4, and y equals x squared, and has squares perpendicular to the x-axis as cross sections. Okay. You can use your graphing calculator if you don't know what x squared or any of these functions look like, but essentially the way that you're setting this up is you have boundaries. Y equals 0. Y equals 0 is the x-axis, right? Y equals 0 is right here. X equals 4 and y equals x squared. Well, y equals x squared looks like this. And so I've taken care of this one. I've taken care of this one. Now I need to draw x equals 4. X equals 4 is just going through 4. So this is x equals 4. Okay. And it's asking us find the volume of a solid that's enclosed by this region right here. Okay. So again, apologize for my artistry, but if I were to draw this in 3 dimensions, and we're not going to do this for every example, but I'll just show you at the start like what this all is. I would be drawing it like this, right? Okay. Now what it's asking is, it's telling you to cut this cross section with squares, okay, square shapes. So that means like if I draw a little square right here, that square is going to have a little depth to it, right? I want to basically take a square and knife through this section, and there's going to be like an infinite amount of these squares that I'm going to cut. Okay, so you would want to say you want to take the area of this times the depth of this. So let's find what the area of that cross section would be first. Okay. Well, the area of a square is just going to be basically the length of the base times the height, right? Well, the length of the base is just it's going to be different, right? This square is going to be smaller than this square. So basically this base is going to change, but this distance right here is always going to be x squared. Okay, from here to here, here to here, here to here, that distance is always going to be x squared because we're on that graph. Okay, so I'm going to say x squared, but then the height of that, right? Because we want to take the surface area. So this times this. Well, if it's a square, your length and your height are always the same. So it's x to the 4th. Okay. That gives us the area of that square knife that's cutting through, the surface area. Yeah. Yeah, so we want to know, we have this square that's like cutting through this section, right? But in order to take the surface area of that square, we want to do length times height. Well, that length is represented by the distance from here to here, here to here, here to here. That distance is always going to be x squared because that's the graph that we're reaching up to. And then since that distance is x squared, if it's a square, the height's going to be the same. So length times width gives me x to the fourth. Okay.
So what if like the shape didn't start at 0? How would you do that?
We're going to do that in like the third example. It's a little bit more challenging, but we'll get to it. Okay. This gives us the surface area of that square, but we want volume, so we want the depth of each one of those squares, which is going to be dx, right? Because we're going in the x direction. So you would say volume is equal to the integral, and we're going from 0 to 4, right? 0 to 4, so it'd be 0 to 4 of x to the fourth dx. Now remember that dx gives me this, gives me that depth. So this would give me volume, okay? That's what you plug into your calculator to get the volume of that cross section or those cross sections. Let's do that and see if we can all get the same answer. By the end of the period, you'll be able to do these really quick. You'd want to go to, since this is the first one, I'll do it with you. You'd want to go to math 9 gives you the integral function. So math 9. And then I'm going to go from 0 to 4, x to the fourth dx. Well, 4.8. And be careful, this is volume. So on your quiz and on AP questions, make sure you put your cubic, your units cubed. Now this doesn't say inches or feet or anything like that, so we just write inches cubed or units cubed. Okay. All right. You're not always going to have a square that cuts through this, right? Your knife could be in the shape of a rectangle, a triangle. This is what you're going to be able to use on the quiz. This is going to be a really good shortcut for you guys. I know it's a lot, but if you write this down, that's going to basically get us through the next 3 or 4 examples. I knew it was going to be a lot of writing too. That's why I wanted to skip the AP at the start. Yeah. Yes. Yeah. This should say, oh, it's not letting me here. It's just square root of 3 over 4 times s squared. Yeah. S is always your side length, if that helps anyone. S refers to your side length of your shape. Let's see where everyone's at here. Looks like we're almost all done. All right. All right, let's do another 30 seconds. If anyone wants me to go back during work time today, I can always just put this back up here. Try and get us through these sections and notes by 1 o'clock. So that way we can take a break and have some practice. Okay. All right, I think actually this example is pretty similar to the first example we just did. Actually, no, it's not. It's equilateral triangles. So let's do that one. We are, all right, so it gives us the base of y equals x over 2 bounded by x equals 4 and y equals 0. So I think like that whole top part is what you want to get down first, and then we can start drawing it. Okay, you don't necessarily have to write down the hints because we already had that on the previous slide. On all of these problems, it's always a good idea just to graph the y equals part in your calculator just to know like what you're looking at. Just to save you some time though, y equals x over 2 looks something like this. It's just a linear straight line, okay? So this is y equals x over 2. Now x equals 4 is going to be right here, x equals 4. And my third boundary is y equals 0. So that's this base right here. So now again, once again, it's asking us for these cross sections, okay? But now, again, just to try and show you guys what this equilateral triangle would look like, if I drew this, let's see, I draw this like this, and this is what, x equals 4. When I draw this triangle in here, instead of a square knife, it's going to be a triangular knife, and it's going to have some depth to it, right? Call that depth dx, because we're going in the x direction. And there's going to be an infinite amount of those triangular knives cutting this up, right? It's asking for volume, so let's just plug it into this equation. We can say, well, actually, first, let's figure out what our S is, right? Because we want to know what is our side length. Well, our side length is just the distance. This is in a different color. Our side length is just the distance from here to here, right? The base of that triangle, and that's just x minus 2, right? From here to here, here to here, no matter where I'm at, this is always going to be x over 2, okay? So then you would say volume is equal to square root of 3 over 4 from, what are our boundaries? We're going from 0 to 4 of s squared. Okay, so my side length is going to be x over 2 squared, and then times our width, which is dx. And so that's what you plug into your calculator. You can keep the square root of 3 over 4 on the outside. We all come up with the same thing. Jacob? In these first couple cases where we're bounded by like the x-axis from here to here is always going to be, it's always going to be that function. Okay. However, if we have like something up here where we have like two different things going on up here, then it's going to be a little different. Okay. But if it's always bounded by the x-axis, then yes. Okay. Should get, let's see, 2.309. Make sure you can get that. If not, let me know. Right? Okay, let's try one more that's a little bit more difficult, and then we'll try one where we're actually cutting it in the other direction, perpendicular to the y-axis instead of the x-axis. So I've got like two more, I think two more for you guys. Okay, everyone's good so far? Okay, let's say y squared equals 2x, so we're going from 0 to 2. And our cross section is going to be semicircles perpendicular to the x-axis. The next, after this slide, I'm going to do some that are perpendicular to y-axis. So it's going to change a couple things, but it's either going to be perpendicular to the x or perpendicular to the y. Okay. Just a heads up, always get your function that they're using in terms of y equals. So this should actually be written as y equals plus or minus square root of 2x. I don't want y squared, I want y equals. Okay, and I think that might make more sense once we get into the problem. Okay, if I were to graph that, it would look like this. Okay, and we're going from 0 to 2. So here's 0. I'm just looking right here. It tells us from 0 to 2. So let's say 2 is like right here somewhere. Okay, now we're going to slice through this, but instead of a square or a triangular knife, we're going to use a semicircular knife. So it's going to be hard for me to draw it in 2 dimensions. So just again, to show you what it would look like in 3 dimensions, let's say this is my function. If I were to slice through it with a semicircular knife, it would look something like this. Would have some depth to it, but think of it like cutting through that, right? Okay, so now the question is, okay, so S is going to be the distance. So this area of a semicircle right here, this is, I mean, area of a circle, 1/2 pi r squared, right? But it's cutting everything in half because it's a semicircle. So instead of pi r squared, it's 1/2 r squared over 2 squared. Okay, so the S is basically my radius. Okay, from here to here is positive square root of 2x. From here to here is also square root of 2x in the other direction. Okay, so that's why this says positive or negative square root of 2x. This is the positive part, this is the negative part. Okay, so if I were to write my volume formula, I'm looking at this one right here. I can write it. I would say volume is equal to 1/2 pi, the integral from 0 to 2, right? S is my radius, right? So my radius is square root of 2x. So I would say square root of 2x over 2 squared, and that's dx. Okay. You can really, I mean, you could leave it like this, plug it right into your calculator like that. If you guys wanted to distribute that too, like distribute that power, you could do that and simplify it a little bit more. But I mean, technically, if you just plugged it in like this, we should all get the same answer. Let's see if we get that. It comes out to, I'll do it with you guys just to double check. So I'm going to do 0.5 pi times math 9, 0 to 2, parentheses. I guess you would have to be careful with your parentheses here. You'd have top would be square root of 2x. I'm getting 1.570. Another thing you could do to make this easier for you, you could write it like this. This would be, and this would be 2x over 4 dx. You could do that. I would just distribute that too, so you don't have to worry about parentheses as much. You should get 1.570. Yeah, Jack. I think I followed the first part. Can you say that one more time? Oh, if it wasn't a semicircle? You would do, if it was a square, you would have to, right, yeah. I don't know. I think we're gonna do, I think on later examples, is kind of like what you're talking about. You basically have to add like your two squares up, I guess, best way to say it. Okay, all right. I know I'm trying to get us through this in a timely fashion because I know it's a lot of writing. We've done everything that's perpendicular to the x-axis. I do want to show you one example where you're cutting perpendicular to the y-axis because that's going to change a few things. This is just like a comparison. You probably don't have to write too much down on the left-hand side because we've been doing this, but you do want to note, I guess I'll let you write this first, then I'll point out some kind of key items. The biggest thing I'll point out here is your function is in terms of x when we've been doing it perpendicular to the x-axis. Your function is now going to be in terms of y when you're doing it perpendicular to the y-axis. So also your boundaries, let's say this is A to B, your boundaries are going to flip now to where you have like A to B. You're cutting this way now instead of this way. Yeah, Annie. So you said as it goes to the right. I don't want to, I'm not sure I understand. Let me get through one problem and see if it answers your question. Okay. All right. As you're ready, we'll do one last one. Okay, again, I can always come back to this if you need me to. All right, we're gonna do y equals square root of 4 minus x squared. Our boundaries at y equals 0, square cross sections with bases perpendicular to the y-axis now. Okay, if you guys were to graph this in your calculator, square root of 4 minus x squared would look something like this. Okay. Now it says square cross sections perpendicular to the y-axis. That means your cross sections are now going to look, I know I didn't draw in 3 dimensions, but basically now you're cutting this way. Okay, so your boundaries need to be from here to here instead of here to here. Okay, the first thing you need to do though is switch. Remember, we want to switch and write it in terms of y instead of in terms of x. So basically you need to solve for x, right? Because that's going to help me start finding the volume. So if I have right now 4 minus x squared, I want to solve for x. So I would square both sides. And I'd have y squared is equal to 4 minus x squared. I would bring my x over here and I'd bring my y over here. So I can just write it as x squared is equal to 4 minus y squared. So now let's get it in terms of x. So let's take the square root of both sides. X equals plus or minus square root of 4 minus y squared. Okay. Okay. So to find our volume, we would be integrating. Let's write volume equals. Now this is s squared, right? Side length squared, length times width. But our boundaries now are going to be in this direction, in the y direction. So we're going to go from 0 to 2. How do I know it's 2? Because you can do, like, you can check in your calculator. Like once you graph it, you can find that y-intercept. Okay. Okay. So what's this side length? Yeah, Misha. Well, it depends on the function, right? If it's like 9 minus x squared, it would be 3, or yeah. Right. Yeah. Okay. So we just have to write our side length squared, right? Length times width. So the key here, though, is our side length. This is plus or minus square root of 4 minus y squared. Well, this represents positive 4 minus y squared, square root. This represents the other side, the negative side of it, 4 minus y squared. So really, when you add those two together, that's going to be that whole side. Your whole side length is 2 square root of 4 minus y squared. Right? This plus this is 2 square root of 4 minus y squared. Did I lose anyone there? Don't be afraid to ask. Did I lose you, Annie? Okay. So x is equal to positive or minus square root of 4 minus y squared, right? Okay. That represents the distance from here to here. Okay. But I don't want that distance. I want this entire distance. So that's why I multiplied it by 2. Okay. So then I'm just plugging into this formula now. It's going to be 2 square root of 4 minus y squared squared, right? It's s squared, so I need to square the whole thing. And this would be dy, because we have a depth to each of those shapes. And that's what you want to plug in your calculator. Give that a try. See if you can get, I got 64 over 3, so that comes out to 21 and a third.